Hello everyone, today I'll be showing you homework 6 hints. First, let's read the data. So I have a housing data and I'll show you what the housing data is. So I have a lot area, I have living area, garage area, year built, basement, and so on. So what I'm trying to do with this data is that I'm trying to predict the sale price based on the housing characteristic. But suppose I want to build, so I have a data when the house is built. So I want to build my model for house that is before 2001 and then predict what is the sale price for housing that is that's built after 2001. So I need to split my subset. How do I do that? So I will use the function subset. And then what you put is that this will be your data set. It should be a data frame format. And then the second part to it should be your condition. So what are you trying to do? For me, it's like I want houses that is built before 2001. So I will put the column names, year built, less than or equals to 2001. And then this data set, the train data set, it's a data set that I will build my linear model and get my beta node and beta 1. If I build both, then I cannot do prediction later. So if you look at the housing data here that has been subset, you'll see that I will not have a data that is after 2001. And if I do my test data, then it will be all the year built after 2001, as you can see here. Okay. So next, so suppose that I don't need this year built as my predictor because it means nothing. It's just a label for me, and I want to change it to my row names. As you can see here, row names are just numbers here. So then I will do row.names of housing data. So if I do this, then it will just return me the current row names, which I do not want. I want to change it to year built. So if I do this, now if I run this, my housing name changes. And I'll do the same for test and I'll show you how it looks like. So now you'll see that the row names is changed to the year built. And this way I can get rid of year built but also still know what is this line, which year it is for. So now I'll get rid of my column year built for both my train and test. So now as you can see, there's no more year built, but then I still have my row names to tell me which year the house is. Next, we want to find the best subset, so to know which predictors are good. There are two ways to do it, and I'll show you both, and you can use whichever that you want. The first one is from a package called Leaps. Load it, and if you have not installed it, then you can do the install packages. And then how you do it is very similar to linear model, where you do a formula and then tell it which data set you're using. And there's a trick here. Previously, you only have one predictor, so it's easy. But now, for my case, I have 9 predictors. I don't want to be writing all my predictor names. So normally you could do, so if you do names and the data set, it will return the column names. So one way you could do it is if you could do one by one. So you can do one predictor, and then plus will indicate that you're including all to your model, and then you can and so on. So this way it's inconvenient because you have to write 9 times. But if I just do a dot here, what it does is that it takes all the predictors or the columns that's in here except your y variable here, and it will just fit it in. So that's a nice trick here. So run that, and then I will do a plot. You can do a summary, but it doesn't really provide a helpful one. So you want to pick a model that has the closest to your number of predictors. So now you have 1, 2, 3, 4, 5, 6, 7, 8. So then 7 predictors and 1 y variables. So then I will either pick 6 or 8 as my model. You can also do r square, and then you will pick maybe the most r square, and then this means that I include all the variables here. You can still get a 0.48 r square without this basement finish. So then this is how you pick your variables. And for the other one, the library mess, so professor has talked about the forward and backward selection. So what you have to do first is you have to fit in the model, fit everything in. So you don't care about what it is, you just fit a model first. And then what you do is that you use this function step AIC, put your linear MLR object here, and then you can tell them how you want to select your variables. So if you're not sure what is the direction here, you can do step AIC. Now it will tell you there is both backward, forward, and you can do whichever you want. So suppose you do I do backward. So then it will tell you step by step how they remove it and which one they remove it. And then if you do step ANOVA, this will tell you the final model. So then it will tell you what is the initial model, and then it will tell you what's the final model. So the model that they chose is this one, with lot area, gray living area, garage, and total number of rooms above the ground. So so you can pick whichever that you want, and then fit that model. So then let's say I decided to choose this as my model, then I will just do fit another one, LN, and then I'll do best linear model. And I can just copy and paste and then tell which one is my data. Housing train. And then I can look at the summary of the housing to see what's my R-square. So right now my R-square is 0.466. So let's look at the full model that I fit in earlier. Oops, not this one. This one. So if I run this, you'll see that your R-square is 477, but your adjusted R-square, which you should be looking at for the multiple linear regressions, is negative. So if you see the formula, it should not be negative. So the reason why it's negative is because you are trying to put too much predictors, and it's not really explaining much. So when you see a negative adjusted R-square, that means that you have to really look into your predictors and remove things. So for this one, we'll see that after removing some, which is we'll see that the adjusted R-square is still terrible, but it's better. It is explaining something, but it's just a terrible model. Okay, next, part of your homework is to check for linear regression assumptions, and I assume by now that you should know how to do it using the 4 different plots. And if you're not sure, refer to the previous video. The only thing that I will add on for checking linearity is that previously you can just do a scatter plot between your response variable and your predictor, one predictor. But then now you have, let's say you have 9. So there is a shortcut for that. Rather than individually do a 9 plots, you can do pairs, and then this will be just your data set. If I run this, you'll see here, if you zoom in here, you'll see a bigger one. But then this is basically a scatter plot combination of all the variables that you have. And then you'll try to see if there is any linear pattern or non-linear pattern from here, like sales price with, I don't know, let's say, I can't really see here, but you can just look at your scatter plot and then decide if there is a non-linear relationship or not, or linear relationship. Next, checking for multicollinearity. So suppose that I did not do any best subset selection, I just do the full linear model. So if I run this, I see that I have 2 variables that I need to be careful about. So the garage area has above 6, above 4, and then garage cars has above 4 too. So as mentioned in the lecture, that if you see anything after 4, then we should start getting worried. So suppose that, so what you can see is that if I remove this, this is without the garage area and garage cars. I run this, and you see that there is an improvement in the adjusted R-square. And if you remember earlier, when we do the full linear model, the adjusted R-square is negative. So you can see that there is some effect in removing multicollinear predictors. So that's how you would check for that. Next, checking for influential observations. So there is a difference between influential observations and outlier. Outlier is happened because there's some kind of error. Let's say if when someone put in the data, they forgot to put in a 0 or something like that, then that's an error. Influential observations is it actually happens. It's just that it doesn't follow the trend for whatever reason. So how can you know for that is plot your linear model object and see there's 4 different plots. So from here I can tell right away that this 1977, there's something wrong with it. Let's look at the next plot. And I still see that it kind of follows the normal polyplot, but then we see that 1977 is really out. 1989 is something that we need to be careful about too. And then, and this one too. So there's 3 different points that we need to look up, but mainly 1977 because it's way out here. So there are several ways we can do it. First, you can do a Cook distance. So Cook distance will tell you if that is an outlier or inflection point. So I do Cook distance of my linear model. And then what I see is that if I see anything that is close to 1, the value, if it's close to 1, then it's an influential observation. But if it's not, like for example 1977, that is giving us problem, it is a very small number. So it is unlikely that this is an influential observation. It might be an outlier. Another different way to do it is using this function, outlier test from the library car. So if I run this, it will tell me right away that this 1977 is a outlier. And how you test it is through the Ben-Ferny test. You don't have to know the test is, but you just need to know how do you get them. So then I want to get rid of 1977 because it's an outlier and my R-square is only 47%. It's really bad. Okay, so how do I remove a row from my data set? So first, as you remember earlier, we have our row names, right? So this is when it's come handy. So I want to remove this 1977. So when I do row names, it gives me a vector of character. And then I want this double equal signs. It's a logical statement. So what I'm trying to say is that I want to find in this row names that is equal to 1977. So if I run this, it will tell me that the first one, as we can see, 1990 is not 1977. So it will give me false, 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 and then true, which is the 4th one, which is right, and then false, false, false. So what you do is that, and I'll show you. So this is your data frame. So so you have the left and your right here. So this is your row numbers, and this is your column numbers. So if I put this, I'll name it something. Let's say location 1977. Store it here. And then I put it in my row names. So if I run this, you'll see that it returns the row that has 1977. But then I'm trying to get rid of this. So what you do, so because this is a logical statement, doing a what do you call this? Exclamation mark will negate that. So if I run this, you'll see that it will print out everything else that is not 1977. So what you can do is that now, since if I run this this row number can take numbers, or it can also take a logical statement. So if it's false, then it will not take it. So then how you remove it is using this housing train. So I want to put a exclamation here saying that I don't want a location 1977. So I run this, and then you get the without 1977. But then remember, if you just run this, it will just be printed out and not saved. So then what you want to do is, so I already did it here. So you will do the same, and then you will store this. You will kind of replace the whole thing in here. So if I run this, and if I look at my housing data train, now if you see, I don't have 1977 anymore. So it was 15 and now it's only 14. So that's how you remove it. So now that I've removed it, let's try to fit the model again. So using the same data, I'll do maybe change the number so that I can show you the difference. So now I run this, and let's look at the summary. My R-square has improved greatly. Now my adjusted R-square is over 90%, and previously is barely 40% or 20%. So then you can see how important it is to remove and not remove an outlier. And sometimes if you remove a influential observation, your R-square might actually you will not have a as meaningful model. Next, prediction. So now you have already your models, and then you can see what is your equations, right? This is your beta naught. This is your beta x1, x2, beta 1, beta 2, beta 3, and so on. So you could easily write your equation like this, and then 3824.838 plus 2.922 x1 and so on. And then if you want to predict this new data, this data set, then you will take, let's say, your x1. So you will take 2.922 times 6240 plus 101.573 times 1342 and so on. So you could do that manually, or if you do predict and then you provide your new data here, which has the same column names as your when you fit this model. Before that, let me do this first. So if you run this, then you will get all the values. But then let's say you want to do interval. If you just add that, it will conveniently give you the 95% confidence interval. So that's all I have. I think it's quite straightforward. And again, if you have any more questions, please post it on Piazza. Thank you.